Hi, Abby.
All right, we're going to go ahead and get started with April's Grease Thief Thursday. Thank you for everyone joining us here on Digital Samba and everyone over on our YouTube Live as well. Rich today is going to be covering the topic of achieving sustainability for grease lubricated machines. And so, and Rich, take it away.
All right, thanks, Abby. Yeah, it's about sustainability, and this is really a topic that a lot of folks are paying closer attention to. So I wanted to take this topic and then apply that to our machinery, and more specifically about greases. And so, here's kind of my outline. And I just finished watching a launch of SpaceX. Um, and of course, Elon Musk, the head of that organization, doing some really interesting things there. But I'm going to make the statement that Elon Musk is destroying the grease industry, and then I'm going to talk about how we could mix greases without making a mess, and why. What are the reasons behind us wasting grease and polluting the planet? My statement is machines don't die, we kill them. And a lot of times it's because of the way with which we approach our lubrication practices. So I'm going to talk about how we can avoid that and give some case study examples for that. So, so when we talk about optimization and sustainability, we should really start with a picture of the just how big is this market and what are we talking about with grease. And so I just got a copy of the 2021 summary from Lubes and Greases magazine, which does actually reference this material from NLGI. And you can see that here in North America, the grease consumption, if you will, production consumption, is 373.9 million pounds of grease annually. And if we then scope that up to the global figure, we're talking about 2.6 billion pounds of grease being produced and then obviously consumed. You can see from these charts that the majority of these greases are lithium greases. If we look at the global percentage, we're talking about 51% being conventional lithium greases, and then lithium complex greases comprising 21%. In the US, there's a little bit of a skew there. It skews higher with the lithium complex greases, but still a substantial amount, approaching 75% or three quarters of the world's greases being lithium greases. And so how does that factor into it? And this is where I make that statement about Elon Musk, and because he's also at the forefront of the EV development, and the EV development or electrical vehicles relies heavily at this stage of development on lithium batteries. And so there's this huge global demand for lithium that is increasing every day. It is then also affected by the lithium supply itself, which is discreetly deposited in certain areas around the globe. So, not kind of a universal product, but needs to be mined and sourced from some of these locations that you find lithium. So, you have kind of these combined forces putting a lot of pressure on lithium, such that what has in the past been a very economical solution, the lithium greases, those prices are going up, and they're going up quickly, and in many cases are simply not available. So I have people reaching out to me and saying, hey, you're a grease guy and you work around greases. Do you know where I can get my hands on 20,000 pounds of lithium complex grease? And the answer is no. And a lot of the suppliers are struggling with that as well. So, is it really a sustainable situation that we're in today with this heavy dependence on lithium for greases? And I'm going to make that argument that it is not sustainable. So basically, Elon Musk has said Tesla will essentially need 100% of the world's lithium supply. How much does that leave over for grease? The answer is obviously zero. So the choices are: we use 75% less grease. We basically reduce that grease, or we diversify, right? So we reduce the demand or we diversify into other products. So what can we do? Where can we transition to? Well, calcium could be one of those solutions. Calcium sulfonate complex greases, they do have some great advantages, and they don't have quite the demand issues that are pinching a lithium as a grease solution. But if we do that, if we change, we say 75% of the grease out there is lithium based, and we're going to lose our supply of lithium, then we have to switch to something else. Grease, by its very nature, is designed to stay in the machine, to stick and stay where we put it, so it's not easy to get out. So as we go to alternative problems that could be calcium sulfonate or some other grease, it raises this issue about how do we manage the billions, if not trillions of dollars of assets that are out there that are lubricated presently with some sort of lithium grease or something that we move away from. And so we can evaluate those mixtures that we know we have to create as we transition from one product to the next. Even if the greases are made with the same base oil and thickener type, they may be incompatible. So that's something that we want to keep in mind. If the greases are incompatible, mixing could lead to significant changes. It could be changes in grease flow. It could be shear behavior. And bottom line is we end up with inadequate lubrication, and we threaten the condition of the grease lubricated machinery. So here is a picture of a compatibility chart. A few folks out there have more recently taken to question these charts and even attack them. I just reposted something from Chuck Coe this past week where he called the compatibility charts dangerous, and they certainly are. And in a study I did a few years ago, I found 17 different compatibility charts, and none of them agree with each other. So we've got some issues, and this is not the place to go, not the place to start. So that's what a compatibility test can do for us. So if we know we have to switch from one product to another, we have to address that compatibility issue, and testing is really the way to do that. So here's just a little bit shared stuff that we do in the lab here for the compatibility test. We start by taking a ratio of two different products. Here you can see that they have different colors. A lot of greases have colors; they're dyed, and that tells us about their basically what dye has been added to them, and that's about it. But it is helpful in being able to visually distinguish these greases. And so you can see we've got more of the darker grease than the lighter grease, and we get a mixture there that's blended together, and then we start testing that mixture. There is a test for this, a standard, and it's an ASTM standard D6185. And this standard has you mix these different ratios together and then run a couple of tests, namely the cone penetration test and the dropping point test. There's another test in there, which is a storage stability, which is also a cone penetration type test. And if you read the standard carefully, it says that these are just kind of the first level of testing, that typically you have to go beyond this into a second tier of testing to fully evaluate the compatibility. Unfortunately, most folks will, ask for this test to be performed. They'll get results just on the cone pen, the dropping point, and the storage stability, and they'll say, oh, it met the requirements, therefore they're compatible. And that's not what the standard says. So, there's a working group at ASTM that's working on this standard, that's submitting some alternative ways to approach that. Some of these have been discussed, that are being discussed, include the methods that we're using here at MRG Labs. So I'll share that with you. We see these different baselines being tested, as well as these like 90-10 mixtures, sometimes 75-25, and then of course a 50-50 mixture that's going to see what happens as we transition from one product to the next. And then in our testing, our compatibility studies will then mix and verify that mixture and those ratios using FTIR to look at the organic constituents and the differences in the organic content of those greases, as well as the elemental differences that we'll see in rotating disc electroscopy. So the rotating disc electrode spectroscopy. And then the mixtures and these baselines are packed and worked on a test stand for 72 hours. So we have an 8 bearing test stand where each bearing is run and loaded the same. It's done at a medium speed, I guess you'd say, around 1800 RPM. And that's done for 72 hours. And that's as compared to the comb pen tests, which are like 60 double strokes or maybe even 10,000 double strokes for storage stability. But in that 72 hours, we're getting nearly 30 million mixing events. And so it's not an immediate effect. It's not like these two greases touch and immediately some reaction takes place. It's a physical, rheological, and a longer term shear down of the grease when it is mixed together that we're looking for. So it's important to have a longer period of mixing and working of these greases to allow those potential issues to arise and be measurable. And so that's why we do this for a more extended period of time. The 72 hours enough? Well, it may or may not truly show you what's going to happen 1 month, 3 months, 6 months down the road. But we're then going to measure pretty precisely the rheological properties so we can look for more moderate changes. Typically the grease, when it comes out of there after 72 hours, is not what you would say is unfit for use. But there's been enough measurable change at that point to say these two greases are not behaving as if they were just two of a similar product in the same space in these ratios. They're actually changing. Their physical properties are changing. Their ability to resist shearing is changing, and that's measurable over that period of time. Here's some of the results that you might see. Here's a mixture of greases that passed the test. You can see we're looking in 3 areas: the recoverable compliance, the G prime or the storage modulus, and then the yield stress. And each of these will have values that measured in pascals or in percentage for recoverable compliance that will have values that will likely be somewhat different between the two greases. Remember, when we're specifying greases, these kind of properties and performance are typically not specified. It's just going to be an NLGI grade, perhaps a base oil viscosity, certain types of additives, and so on. But here is where we can look at how do these things change. And so we look for values that fall near the expected average values that we would see from mixing these greases together in these ratios. And you can see the 50-50, 90-10, and 10-90 mixtures here. And what we have is a calculated expected value at those mixed ratios. And you can see that these greases line up very, very close to those expected values. So there's not a big change here for these two different greases when they get mixed together in those ratios. That's a pass. And so, how is this helpful? A passing test can be very helpful because it can be something that says to someone that has to switch over products. And remember, it might not just be about one machine. There may be a switch over of products that affects 100 machines. And if we get these kind of results, now instead of having to create maintenance work activities to dig all that grease out of all those machines before we put the new grease in, we can say, no, we've tested them. They're compatible. We're going to transition from A to B, and we're going to be good going forward. And of course, with that, there's also been this evaluation that the second grease is also suitable for the application. It has the appropriate base oil viscosity, the type of oil, the additives that are necessary, the consistency, and so forth. So that's a pass. And if this is not done, you're kind of taking your chances because you don't always get this result. Other times you get a significant and somewhat unexpected change in these values that's going to affect how that grease behaves. And if someone just says, well, I asked the manufacturer and they said I could use this grease, or I pulled up a compatibility chart and it didn't say that they were incompatible, so I'm going to proceed. It is really proceeding at risk. And the risk is that you're going to do this, the grease is going to interact, you're going to have a problem, it could harden, the grease could soften excessively, it could leak out of the machine, it could cause a separation between the base oil and the thickener. And all of these could result in catastrophic machine failure. And if you multiply that through a facility, the impact can be quite significant. I recall that we did a compatibility study that was basically for one machine in one facility. It was a 4,000 horsepower, very old and almost unique electric motor in a primary metals application. And they talked about there was a 12-month delay on being able to source a replacement for this. So they basically needed to be very confident, and the product, the grease that they have been using, was off the market, wasn't made, so they had no choice to transition. So they gave us the first product they gave us looked something like this, where you had significantly different values. You can see where the mixtures are supposed to fall here, and the values are like double that. For example, for recoverable compliance, they're outside of the acceptable range for the storage modulus, and some of the yield stress values are quite a bit different. In that case, the first grease looked like this. The second grease looked similar that they tried. They went on to a third grease. We said that grease looks a lot better, but it's still some measurable change. As they finally got to their fourth grease, it looked something like this. And then they had a lot of confidence that they could move on with this critical component. So that's what the grease compatibility study can do for you. So if we have this reality of a market that is going after the same materials we're using for greases, and it's inevitable that we're going to run out of lithium grease, that supply is going to be pinched off, we have to be thinking, how do we prepare for that coming transition? How do we have the confidence that the products that we're going to use in place of it are going to be suitable, or at least know that they're not? And we're going to have to plan around transitioning by completely changing bearings or completely tearing equipment apart, pulling end bells off of motors. All of that, if we're not prepared for it, we're setting ourselves up for failure. So let's look at another component of the grease supply and this demand that's in the marketplace for lithium and other greases. And it comes down to the question of why are we replenishing grease? What are the reasons behind that? And so one of the issues is about oxidation. Grease in machines, it could be in bearings, it could be on gear surfaces, what have you, but it's typically subjected to what we call oxidation stressors: heat, air, water, metal catalysts. These are all chemically attacking the oil to break it down through this mechanism of oxidation. So over time, and when we set up re-greasing frequencies, a lot of times it's based off of these variables. What's the temperature that the bearing operates at? What is the vibration that might shake the grease out? What is the water level, the particulate level, the dirt that's there that we're trying to flush away? So all those things. So oxidation is one of them. Another is shear down of thickener. So over time, as this bearing, roller, gear, as it works through the grease, it's breaking up these fibers in that thickener network, and over time making it softer than it was at the beginning. A really good grease for a long-term application has a high shear life, basically, so that it can take that on. But eventually, more quickly for higher speed machines, because you get more of those shearing events, and then other factors would accelerate that as well. Eventually it breaks down. The grease is no longer has the consistency it's needed to stay in place, and we need to replenish it, push the old stuff out of the way, get the new stuff in there. So oxidation, shear down a thickener, separation of oil happens over time. So and it's really the oil that does the work of lubrication, and the additives in it. So we really need that oil to stay there in place, not to leak away, not to run away from the bearing, end up in the louvers of the motor, what have you. So before that happens, We're adding fresh grease. We're replenishing that grease. We may over time lose some of the wear protection. We have greases that are anti-wear or EP additives. They are finite in terms of being able to provide that protection because the additives are consumed in boundary lubrication. So there's a finite amount that we start with, and we have to replenish that. The grease can harden over time. And then again, this flushing process of flushing out contaminants of water, dirt, and this other contamination of grease mixing, the wrong grease being there. So these might all be reasons that we would be replenishing the grease. I'm going to make the statement that the default state of greasing is over greasing. And why is that? Well, if we are under greasing, so whatever frequency that's been adopted for an asset, if it turns out that it's an inadequate quantity or it's being added too infrequently to address the issues, what is the result? The results are very obvious. We end up with machine damage. We have a failure of the machinery and a loss of function. So the reaction to this under grease state is to add grease more often, right? That machine, that critical machine failed. Someone says, find out what happened. They open it up, the grease is dried out or there's not enough there. Then they say, okay, grease it more often. You guys did not grease it enough. So we end up going, the pendulum swings in the other direction. Versus if we are in a default state of overgreasing, what are the symptoms? What are the consequences of that? Well, the machine overheats. And, it's within some range that it may continue to operate for a long time, but it maybe isn't obvious that that machine doesn't need to operate that hot. Instead of being 160 degrees, it might be 165 or 170. So that's a possibility. You've got cleanliness issues, meaning that the grease is dripping on the floor or whatever. Well, we've got people to wipe that up, right? So that's recoverable. Or you've got this picture that you see in the lower right where so much grease has been added, it's going through the shields and it's in the windings of that motor. Well, you're not going to see that until somewhere down the road and the motor set off to a motor shop. And they're happy because they have work. They're rebuilding motors for you. And unless you're specifically following that work and inspecting alongside those folks to find out what are the issues and feeding it into your process, you don't even realize you've been overgreasing, and it's a cause of premature failure of your motors. Another byproduct of overgreasing is just that excessive cost. We're spending more money than we have to. But there's so many mechanical processes, production processes out there that are generating a high level of revenue for the companies operating those assets, that the difference between infrequent and more frequent greasing from a cost perspective is so low, they'll gladly take it. They'll say, we had a failure that one time when it didn't seem like we were greasing enough. I'll put two fellas out there and they'll be greasing all the time, and we won't have these failures and we'll still be selling product. And then you've got disposal issues. You may have an excess amount of grease that needs to be thrown away, and we just assign that to the cost of doing business. That's the cost of operating that asset. And there's hidden effects inside the machine. So the bottom line is that the undergreasing is obvious. You can't hide from that. It's not overlooked because you lose your process, you lose your machine. The reliability becomes a big issue. It drives us towards overgreasing. And I say that's the state we're in almost universally, unless we do something to find out what's optimal. What does the machine really need? If we can reduce the grease demand, we get ourselves out of some of these issues. So we're in this state of overuse of grease. We're using more grease than we need to. If we can extend the grease life, we reduce the demand. Maybe it's hard to get our hands on the lithium grease supply now and in the coming months and years. But if we reduce our demand by 25, 35, 50%, then we're not trying to compete for that scarce resource. This allows us to eliminate unnecessary lubrication. This goes to manpower issues. Boy, the manpower issues became really obvious during the COVID shutdown, when in some places I know that they just suspended lubrication activities because they just didn't have people around, the people to come to the facility. But if we can eliminate unnecessary lubrication, that goes to labor. We want to raise the awareness of the impact of over lubrication on cost and the planet. And so, there's I want to go to another slide that I have here that's updating these figures, but there are emissions coefficients out there from the U.S. Department of Energy about lubricant, the way lubricants generate CO2. So we'll circle back to that. But if we can keep carbon in the ground by reducing demand for greases, that's obviously going to have a positive impact. And so here is what that carbon footprint looks like. The coefficients from the Department of Energy are 2.3 kilograms of CO2 being generated per liter of lubricant through that disposal cycle. There's an additional estimate I used from some of the same tables and charts of about an additional 0.25 kilograms of CO2 per liter of grease for extraction and shipping. And then you have an additional amount for the additive chemistry and the thickener. So for this meeting, I wanted to attack that last piece. And we know that the additives, I think the exception to this could be molybdenum greases, where that could be substantial if we got into the carbon footprint of mining molybdenum and some of the 5, 6, 8% molybdenum greases that are out there. But I chose to take the kind of the majority of non heavily additized greases, so that I'm just focusing on the thickener in this case. So I took an example, and that's dilithium adipate. And that is recognized by the EPA as one of the highest CO2 producing chemical processes that are out there. And dilithium adipate is one of the feedstock chemicals that's used to create lithium greases, or the lithium soap to make lithium greases. And so taking an example that has a thickener at 10%, so 90% base oil and additives and 10% thickener, we're generating 2.8 kilograms of CO2 per 1 kilogram of adipic acid produced. And if we convert that by that 10% figure, we're generating an additional 0.28 kilograms of CO2 per liter of grease for the thickener. So again, it's going to vary. It's going to vary on the specific chemistry and so forth. But this is a meaningful exercise to arrive at a carbon footprint for greases. I did share with you at the beginning there the figures for grease usage in the U.S. It converts over to 170 million kilograms of grease consumed annually. And if we take the sum of those values, the 2.35, the 0.28, and the 0.25 for the extraction and shipping, we have a total carbon footprint of 2.88 kilograms of CO2 per liter of grease consumed. If we can achieve a 50% reduction in grease demand, and I'll circle back to that figure in a minute, and why I use that figure and why I believe that's the achievable target that we can set for grease demand reduction. That's going to save 85 million liters of grease production per year, or 250 million kilograms of CO2, which is 275,000 tons of CO2 per year, the equivalent of taking 60,000 internal combustion cars off the road. So it's not trivial. And each company that's looking at reasons to improve, this is just one component of it. You're going to reduce labor, as we said. You're going to reduce the purchase cost of purchasing the grease. You're going to reduce the issues related to machine reliability from inadequate greasing, from over lubrication, and the problems that it creates. But there is also a measurable and substantial contribution to the CO2. And so for the corporate responsibility aspect of things, and Abby's going to help me with the terminology there, the corporate responsibility piece. This is something that can be part of that decision and can further justify. In my opinion, a lot of times, again, the output of the process, the asset intensive process, is such that the cost of the grease to make it work, and the difference between optimally greased and excess grease, is such a small component of that there's not an obvious and straight up cost driver that makes us work towards optimization and reduction of use. But when we look at all of the impacts, including CO2 generated by the manufacturing, shipping, and usage process for greases, there's an opportunity to take some pretty significant credit there. So if historically it was pump till you see it come out, right? The squeaky wheel gets the grease, right? Add grease if you have a problem. And the improved method is to have a lubrication round where you've got a number of pumps. Yeah, 3 shots to do the trick. Tell that guy to pick up that grease gun and put 3 shots of grease wherever he sees a grease nipple. That's improved, but certainly not the best. And then you can get into precision greasing, which where we have really valuable tools like a calibrated and clear grease gun where we know what our delivery rate is. We've got color-coded products and fittings. We might even have grease meters that measure the flow of the grease so we know specifically how much we're adding, and then using barcodes, electronic rounds. All these things will drive us towards more uniformity in the greasing process. Uniformity and less mistakes, but not necessarily optimization. Optimization comes about when we have done, we've taken measurements of our machines and we understand what they truly need. And the first kind of level of that is the condition-based greasing that we get from using ultrasonic tools. And this is something that's really on the rise. I have a training class coming up with some folks and in the ultrasound area, and they've said to me that whereas in the past, a lot of their focus for ultrasound solutions, ultrasonic transducers and these tools has been on like reducing air leaks, let's say. It's now greasing. And so there's been a shift to look at this and try to get a handle on this. So it's a growing area. Unfortunately, it takes us a long way, but it doesn't take us all the way to optimize. And that's because you add grease with ultrasound when you detect an inadequate grease condition. So you need to kind of go through this binary state of adequate. Maybe there's a third level in there. I shouldn't say it's just binary, but you go from undergreased when you have metal to metal contact, basically asperity contact, making the ultrasonic noise, to a sufficient film to separate them. And that's in the good. And then if you go too far and you add too much to a particular machine, eventually you get this churning effect and the ultrasound floor continues to rise. But if we truly want to understand what a machine needs and look not just on the establishment of the lubricating film and staying away from an excess churning situation, but all the aspects that govern grease, like the oxidation. Remember what we talked about? Like, what are the reasons that we want to replenish grease? The grease gets to the end of the life because it's been oxidized. The grease gets to the end of the life because the additives are gone, right? The boundary additives like EP and anti-wear. The grease needs to be flushed out because there's been an accumulation of solid particulate. The grease needs to be flushed out because water is getting into that surface. None of those are going to be picked up by ultrasound. It's just grease testing. So equipment sampling and analysis can help us lock in what is that optimal frequency, how can we enhance the lubricant life, and how can we improve the performance of the machinery by optimizing grease lubrication. So the next slide here, what are the factors ultimately that affect that grease life? And there's this tendency, the truth of the matter is our production facilities are designed by engineers, and engineers like to be able to design on the front end all aspects of operation. How should we operate it and so forth. And the challenging part of greasing, lubrication in general, but greasing specifically, is that there's variables. And those variables may change. They may change from design conditions. They may change because an operator of machinery needs higher output or has adopted a new technology or is speeding up their process or slowing down their process. Anytime these things change, so do potentially the impacts on the grease itself and its effectiveness. The factors that affect grease life include the type of machine it is. So basically, what is the geometry of the contact surfaces where the grease are, how are they moving relative to the grease, how's the grease being moved or flung around, the machine speed. The faster the machine is moving, then the more rapidly it's going through these cycles of working the grease and potentially shearing the grease. The operating temperature varies often, and as it does, so does the rate of oxidations, direct related to operating temperatures. The ambient contaminant load that might be higher than was anticipated, and it's something that's very hard to predict. Even if we go to some of these calculation tools that are out there for establishing grease frequencies, they require assumptions. So you'll have to choose from maybe 5 different kind of written out descriptions of what your contamination level is. And it'll be things like low level of mildly abrasive particles, or high levels of mildly abrasive particles, or low levels of highly abrasive. And it's like you somehow have to take every situation and push it into one of these classifications. And really, it's just, guesswork, to be honest. Sealing effectiveness is a hard one to figure out. So how well can the particles and the water get into the machine? And then, something we often don't think about, what is the cleanliness of new grease? So I'll share a story, an anecdotal story. We got a sample here at the lab. It was sent to us by a grease manufacturer, a major grease manufacturer, who had said they're having issues with this particular customer. We'd like you to take a look at the grease that we took out of their machine. We asked for background. What kind of machine is it? And what's the application? They said, nope, just take a look at the grease and tell us what you see. You guys are supposed to know about greases. So we looked at it. We evaluated it. The grease was still in pretty good shape. However, there was a lot of ferrous wear. So we did analytical ferrography, and we separated and inspected the particles. And we found a significant amount of severe gear wear. So it's a very characteristic particle that you can find. And we went back to the grease manufacturer and we said, we found these gear wear particles all through the grease. And they came back and said, well, we're very disappointed in your laboratory. We thought you knew what you were doing. But that sample we gave you was not from a gearbox, and you've completely missed the mark. So we asked for a tube of new grease, and we analyzed the tube of new grease, and we found it full of gear wear. And as it turned out, this facility was in the midst of a failure of their packaging pump, which was a gear pump, so it was a gear transfer pump. And it was grinding itself to death, and it was putting all these particles into that new grease. That's just one example. Other examples are just the grease manufacturing process itself. There is no way to effectively filter grease after it's been manufactured. So what you get is what you get. And if it's not carefully controlled during manufacturing, you end up with dirt in your grease. Water is another issue. Soap thickeners like lithium complex soaps and aluminum soap greases and so forth, calcium soap greases, that soap making process produces water. And then there's a dewatering step. And the truth of the matter is it's very hard to see the water. It's not obvious. It doesn't look cloudy. It's just suspended and distributed through there. So unless we test it, we really don't know what we have. So the condition and cleanliness of new grease has a big impact on the grease life and on the machine life as well, as does the type and quality of the grease. There are some tools, like I said, that can help us determine the lube amount and the interval calculators. There's spreadsheets that we can use. There's apps for this. There's websites from some of the bearing manufacturers. Amri even has these Lube Coach circular cardboard tools that a lot of people enjoy having out in the field to do spot checks and so forth. And again, they can be that kind of next step to get a little bit better about what we're using there. But when we step up to optimization, it requires that analysis. And so in order to do grease analysis, a meaningful grease analysis, we have to start with good samples. So there is an ASTM standard for this. It's ASTM D7718. It is the grease sampling standard. and it's built upon a device called the Grease Thief, and the Grease Thief helps us maintain a purge function with little or no back pressure when used in drains. So you can see on this, and Abby, you can help me. I'm not sure if my little pointer here is visible to the folks in the session or not, but it's highlighted as the body open end on the left hand drawing. That's a threaded design of that fitting, and that can thread right into a machine. That's an 1/8 inch NPT. Oh, there you go. Yep, that's it. That's it exactly, Abby. Thank you. It's an 1/8 inch NPT thread that threads into a lot of, say, medium-sized electric motors. Can also thread into the M10 size metric thread. So that works real nice. You can leave that in the machine and it catches the grease on its way out. Then you also have this stinger probe that you see on the right-hand side. That's a difference there. That piece sticks out, and you can use that with a tool that allows you to go into the machine and kind of feel when you contact that target surface, because we really want that grease to come from that location that has the information about the equipment, about the condition of the grease and the condition of the equipment. So we have 6 different sampling kits that they're shown here: the pillow block kit, the electric motor kit, the wind turbines for robots, for gearboxes, the motor operated valve gearboxes or other gearboxes. And the pillow block kit is kind of our go-to kit. It's we just came back from Ireland, and some folks there in food processing were asking about that, and we said, yeah, that's the place to start. You can take a sample right off of the face of a pillow block bearing, or extract it from a lot of different machines as well. But you start with the right tools and the right techniques, and then you can take it into the next step, which is the analysis piece, the ASTM D7918 standard. And it shows you all these different things that you can measure. Ferrous debris, very simply dropping the Grease Thief into this Poseidon Systems FerroQ device, which we have tested extensively and does represent the ferrous content, whether it is homogeneously distributed or not. If you just have a couple of large particles in one area of the grease, as long as you're capturing them, it's going to measure them and represent them in a parts per million equivalency that allows us to create criteria and to trend and to find the outlier machines that need our attention. We have this die extrusion process, which squeezes the grease back out. And this is really the only technique, what I would say is a straightforward technique for determining changes in consistency for a volume of this size. We can do this with less than a gram of grease. And of course, the cone penetration and some of these other tests, you're talking about hundreds of grams of grease. So we can really miniaturize this process, take it down to a very small target sample size, and obtain that consistency information. Colorimetry becomes helpful in picking up mixing of greases. Linear sweep voltammetry is looking at the antioxidants and how they deplete over time. And so, the die extrusion and the linear sweep voltammetry really critical in optimizing grease replenishment frequencies. If the grease consistency has really dropped off, well, we have to be changing the grease before that point. So this allows us to dial that in. If the die extrusion values are what they were with the new grease, if the linear sweep voltammetry shows a significant remaining life in the grease, and you don't have an accumulation of particulate and water and so forth, then we might be able to extend grease life. And I'll give you some case studies where we've been able to do exactly that. Here's the FerroQ that I talked about. The 200,000 ppm to an oil analysis person sounds kind of nutty. That's a really high concentration, but this happens in greases, especially when there's a problem, because grease is cumulative. And there's nowhere for it to go. It's not being filtered out. It's not settling. And so we really need to accurately measure up to those levels. So it's a consistent and representative measurement. The colorimetry is another valuable tool. We use it a lot for screening process. And we take, and what we found is that the grease needs to be at a set thickness when you light it up, basically, when you're trying to determine its color, because that color or that visual indication can vary based off of the thickness of the grease film. So we set that film, and then we can compare it to the new grease. So you can see an example of severe oxidation where we have kind of a tan or cream color grease that's gotten quite dark due to being oxidized over some period of time in service. And then I think I'm going to struggle with this one. There's a particle counting example here, but I don't quite know how to run the video in the middle of this. If there's time at the end, I'll throw that in there. But yeah, it's a visual process where we extrude this thin film of grease, and then a high resolution camera is picking up the little particles. Now, I don't know, Abby, if you can show again, there's like an oval shaped ring in there, a couple of those. They're actually air bubbles. So the image recognition software can differentiate true particles from air bubbles and just count the particles that are indicative of the kind of damage potential of that particular grease. And then we have the moisture analysis for grease. It sounds pretty straightforward. Everybody can do it for water. It's tricky for grease because water can hide in grease because it's in this kind of clump. So we've developed this method where we take a thin film of the grease coming out of that die extrusion process and then use this Vapor Pro device that uses a humidity sensor and heats that thin layer up, drives the moisture off, takes that in a dry carrier gas to the humidity sensor, turns that into parts per million. And we have seen that we can get up to 10,000 ppm moisture greases with a relative standard deviation of around 5%. So that's very, very repeatable and very accurate in terms of the moisture levels that are there. So let's finish up with a couple of case studies here. The first is from helicopter sampling, and this was a specialized grease sampling kit that was developed for helicopter applications, the hanger bearings, the swash plates, the splines that you find in these drive lines. And the grease analysis data was used to change the maintenance intervals. This is an aircraft that was developed in the early 1960s, so 60 years of operating history. And over that time, there was the initial guesswork of engineers at the time. Pretty good because this airframe is still out there. But you change over time if there's been some discovered discrepancies with the grease, maybe even some accidents or near misses, you end up doing what we said at the very beginning of this discussion, which is defaulting to over greasing. And so we had gotten to a point over 60 years of maintenance where these helicopters are being taken in every 50 flight hours for relubrication of some locations. This study allowed us to reduce the total number of lube tasks from 98 to just 56 for every 1,000 flight hours. So almost cutting the tasks in half, reduced the number of service interruptions in half over that time period. So it's out in the field able to perform its mission, and calculated a cost savings across that fleet of $100 million annually. So a really obvious thing, and keep that 50% figure in mind, right? We almost cut the grease in half. Here were the factors that went into this. So how do we build that condition-based grease optimization? It's by creating the values that will drive the end of the life. So accumulation of wear, consistency changes through the die extrusion, the presence of the different types of metals, particles that are coming from sand and dirt, and moisture levels. And you can see a lot of this was being driven by that oxidation index, some of it by the changes in the consistency of the grease, and some with the accumulation of water. So we went to an optimized condition. Here's another example from robotic greases. And this is a case study where samples were selected from grease lubricated joints on industrial robots. And these are typically fortified with a ZDDP anti-wear and antioxidant. But the issue is these robots are all doing different jobs. And you'll see this when you go through a large facility, very much so in automotive manufacturing, that they have different jobs, whether it's painting or welding, spot welding, lifting up whole car frames, or doing some kind of small fastener assembly. There's differences in load, differences in ambient temperature, differences in contamination, and they are going to result in differences in the life of the grease. And unless we measure them in their application, we won't be optimal. So in this case, we saw a fairly significant reduction in grease requirements. Savings on a fleet of 300 robots was calculated at $70,000 being saved annually. The third example here is for condition monitoring in locomotives. And this was wheel bearing samples, taking samples with that grease thief slim that we showed you there, using the FerroQ to determine the bearing condition, and then setting the locomotive maintenance based off of grease analysis. So there's some other opportunities out there for determining grease life, grease consistency changes, but again, cutting in half the number of failures every month, saving $500,000 on grease testing. The final one here is on wind turbine blade bearings, looking at those. And again, early detection of poor grease conditions, saving $300,000 each instance from proactive greasing and maintenance. So the examples are there. And just to finish up, when we talk about sustainability, I kind of led with grease allows us to have a data-based decision process to move from what's probably, and all my examples back this up, an over lubrication situation to an optimal lubrication. When we move from excessive use of resources to optimized use of resources, we're reducing the demand, we're reducing the labor component, and we're reducing the carbon footprint with some of the values that I gave. So we can conserve energy with optimal viscosity, conserve natural resources through condition-based grease replenishment, also extending equipment life. If the machines last longer, we don't have to replace them with new machines as often. Reduce waste by reducing grease consumption so that waste streams get smaller. We get a greater return on net assets, which is an economically sound process, and then the enhanced safety for everybody involved. And these are all straight out of the sustainability guidelines that come from the UN. So, Abby, that's what I wanted to share today. I know you, as the younger generation, are doing a great job in staying focused on issues like, the planet and sustainability and so forth. And I wanted to take that message into this space and share that with folks today. How did I do?
Yeah, thanks so much, Rich. It was great to hear. It's definitely something that's applicable across all industries, and so it's great to hear how sustainability is focused in the industry of grease lubrication for machinery and all that kind of stuff. So that was really great. We'd love to open the floor to questions. We do have a couple people over on YouTube Live. We have a couple people here on Digital Samba, and so we actually had a question while you were speaking during the presentation. Question on plant-based greases from Paul. While we were talking about compatibility testing and that kind of thing, are those kind of greases viable in these environments? Can you comment on that?
So plant-based, like bio-based. So they're manufactured from plant oils and so forth. Yeah, they can be viable. And what it really comes down to is what is the requirement for the application. What we do find is sometimes when we would transition from, say, a mineral-based oil or a synthetic oil to a plant-based oil, we can get the viscosity requirements and so forth. Sometimes we can get decent life. Sometimes those products suffer a little bit from the oxidation resistance and thermal resistance, and particularly when water gets involved, they can be kind of troublesome. But we should be finding all those applications where they do make sense, where they do meet the technical requirements. But we do have to be conscious that sometimes we have to compensate for some of those poor performing properties with other additives, and the additives themselves might not be as environmentally friendly as we are hoping for. So I would say that there are applications for that, and it makes sense for us to find them, to utilize them. And then when we switch to plant-based lubricants and greases, implement a program of testing so that we can see that they're holding up, and we can even do that economic analysis in that, and take credit for the environmental plus that we get from it.
Awesome. Yeah, thanks for sharing. If there are any other questions, feel free to drop those into the chats on either one. While we do wait for any more questions to come in, I will drop the registration link for our next Grease Thief Thursday here in the chat. We will be having a conversation. It'll be more of a workshop. We're going to do a turbine oil monitoring workshop, conversations on oxidation testing, the importance of monitoring your turbine oil. There'll be applications for steam and gas and hydro, and just having conversations on how to get a good sample as well. So we'll have some demonstrations for those if you're interested. But I just dropped that link in the chat. It looks like we don't have any questions on YouTube, and there's not any more coming in on Digital Samba. Oh, here actually, yeah, there we dropped the link in the chat on YouTube as well. But I think that's about all we have for today. Rich, did you have any last comments you wanted to make on our Grease Thief Thursday for April?
Yeah. For this, you mean for today's, right? Okay. Yeah. I just, Abby, this is not the reason why I started in all this. And, my focus historically has been about, extending machine life and really machine reliability. Is the plant going to run? Is there going to be downtime and so forth? But I think as you look at this more and more, it's becoming obvious that this really is a play for the planet. This is a sustainability issue. And, not all industries are focused there yet, but more and more are. And this is not something to be overlooked. So we're getting the benefit out of this on the very practical side of things, which is reduced labor, reduced costs of operation, extending the life, reduced inputs and so forth. But I don't think we should be overlooking these impacts. One of the things when I was in, and you were there with me as well, when we were in the Netherlands a few months ago, there was a discussion, and the Europeans tend to be a little bit ahead of us in North America on these issues. And there was discussion about the lithium supply, and it came up that they're going to be funding a grease recycling research project to see if you could take used grease and old grease and kind of get the meaningful materials out of it and kind of reprocess it back into new grease. And to me, it's going to be a much easier if we can reduce 10, 20, 30 to 50% of the greases we actually need. We never even get to the point where we need to get into expensive processes to extract it. So for me, the real opportunity is here. We are wasting grease. We are using way more grease than we have to. And it's a dirty business. It's obvious, right? You work around greased equipment, you go home with dirty clothes. But I mean, it's dirty for the planet. And so if we can attack processes like this and say, you know what, we don't even need that much. We can get away with a fraction of that material. That right there is immediate benefits. And that's where I'd like to take things. So Abby, thank you to you for setting this up today. And thank you to everyone that participated. And we'll put this out there, right, so that folks who weren't able to join us, live here can follow up and use these materials. And then how would put folks, if they want to act on anything they heard here today, what's their follow up?
Yeah, for sure. So you just mentioned that we'll have these videos available. So I just dropped that link in the chat, both on YouTube and on Digital Samba. That's how you can kind of share this with people. Or if you want to go back and rewatch something, you heard something interesting you want to hear more about, feel free to check things out there. And then I can also drop a link to our website. Oh, Rich just did it, greasethief.com. They'll have all the information where you can get connected with us. We have our Grease Thief stores that there as well to kind of get involved with the Grease Thief specifically. And yeah, it was a great session. Thanks, Rich. Appreciate it.
Great. So what's next?
Yeah, so next, like I mentioned, we have our May Grease Thief Thursday coming up on turbine oil monitoring. We're going to do a workshop. We do have a few upcoming trainings here, both here in the States, in York, Pennsylvania, as well as an upcoming training in Canada. So those will both be happening this summer. We're going to have MLT1 in Canada in June and MLA and MLT1 in York in August. And those are both the ICML certifications. So if you are interested in any trainings, once again, just hop on our website. It's a great way to get in contact with us. And yeah, thank you all for logging in.
And I want to tease one last thing, is that we talked about it today, that we have a former employee that's trying to set up a steam locomotive excursion for us. And what I'd like to do is put together a seminar as part of that coming out of Reading, Pennsylvania. So look for that. And again, Abby, thank you for setting this up. Well done. And I look forward to seeing everybody next month.
Thanks.